Standard application architecture typically follows a predictable pattern. You have a web server on one side and a traditional relational database on the other. Every time a user requests data, the server queries the database, waits for the disk to spin up, and pulls the information back. To bypass the inherent latency of querying a physical disk, engineers usually drop a key value store block in the middle. The assumption is that this block acts as a simple, volatile cache, a temporary bucket to hold frequently accessed data so the server doesn't have to bother the main database. Limiting this layer to simple caching misrepresents how modern systems actually operate. Breaking open that caching block reveals a multimodal engine capable of transaction queuing, message brokering, and real-time indexing. We can see this engine in action by analyzing how its in-memory structures process geospatial coordinates, orchestrate publish-subscribe messaging networks, and execute complex secondary text searches. Treating an advanced in-memory system as a passive data bucket leaves its most powerful architectural utilities entirely unused. Consider a common real-time operational challenge: rotating ad banners evenly across page reloads, or maintaining a live, constantly updating leaderboard of your most active users. Traditional relational databases struggle with these tasks. Executing a full table scan and sorting interaction counts on every single read and write generates heavy latency at scale. This animated diagram demonstrates the in-memory solution, the sorted set. Instead of sorting data on the fly, the system maintains elements inherently pre-sorted by a numeric score in memory. When we execute the z-increby command against a specific banner, it instantly slides up to its new rank. If we introduce an entirely new element using the zad command, the system calculates its exact position and injects it directly into that slot within the array. Because the structure strictly maintains this order, retrieving the top users is trivial. The zad revrange command allows the system to instantly slice out the top-ranked elements without initiating any background scanning. Shifting the computational burden of sorting to the right phase, the moment of insertion, bypasses the read time latency bottleneck. This logic extends into physical space. Applications frequently need to execute proximity searches, such as finding all delivery addresses within a 15-kilometer bounding box. Using commands like geoadd and geosearch, the engine maps physical coordinates to that same underlying sorted set structure. As we see in this text graphic, the engine enforces strict syntax constraints. Coordinate pairs must be passed as raw numbers, strictly ordered as longitude followed by latitude. The system rejects the invalid format containing any extra text labels. Eliminating extraneous text parsing is a necessary trade-off to achieve the sub-millisecond execution speeds needed for real-time Redis queries. High-performance applications also require stateful system architecture, specifically sending real-time alerts and notifications distributed across multiple servers. This technical schematic shows how Redis natively operates as a message broker. Notice the blue publisher node pushing data into the broker. This capability replaces the need for separate queuing software and many stacks. Look at the central topic queue inside the broker. It acts as a dedicated, named channel. For example, a continuous feed specifically for breaking news. Following the paths from the topic out to the red subscriber notes, we can see how multiple independent services listen to the same channel simultaneously. Operationally, a user simply executes the subscribe command to open a listening connection, while another node executes publish to broadcast a message. This publish-subscribe model decouples the data producer from the consumers. It transforms the database into an active communication hub, routing live traffic. When dealing with high-stakes operations, like withdrawing funds or updating payment logs, execution must be atomic. This terminal simulation illustrates the in-memory transaction lifecycle. Commands are not executed immediately. We open the block with multi, and as we enter subsequent commands, the system acknowledges each one as queued, serializing them for later. Only when the final exec command is entered does the system instantly resolve the 3 queued commands into numbered integer outputs. Error handling happens in phases. If a syntax error or a critical out-of-memory condition occurs before execution begins, the entire queue can be safely flushed using the discard command. However, there is a major architectural distinction here. Unlike traditional relational databases, this system does not support rollbacks once execution begins. If a syntactically valid command is queued but executes against the wrong data type after exec is called, the system will throw an error on that specific line, but it will not reverse the previous successful steps. This is a deliberate design choice. Removing rollback safety nets eliminates massive overhead, trading transactional forgiveness for execution speed. The final capability to analyze is executing complex full-text and parameterized searches entirely in memory. This is handled by Redis, a secondary index module that changes the fundamental mechanics of document search. This schematic visualizes the ingestion phase. On the left, we have raw text documents. The engine takes a string of text and breaks it apart into individual components. Following the blue arrows through the stop word list in the center, the system strips out grammatical noise, like or and maps out the remaining terms. Look at the inverted index table on the right. Terms like cache or data map directly back to the exact numeric document IDs that contain them. Developers use ft.create to define the schema. Once mapped, they use ft.search to query these inverted indices, combining full-text matching with specific numeric constraints, such as filtering for items within a strict price range. This inverted index model replaces document-wide scans with direct lookups. The engine references the term to find its document location instantly. When we cull back, we can see how these disparate modules lock together into a single, unified system. From calculating physical bounding boxes to filtering text stop words, the engine maps complex application requirements directly onto highly specialized data structures. The common assumption that in-memory layers are just dumb, volatile caches is demonstrably false. Modern software engineering requires treating these systems as active compute layers, capable of stateful, high-velocity logic,